Students collect the data below. This was measured in the beginning and that stays fixed. This will be your distance from the source to the first order maximum. Here's the calculation that we did for the distance between the grating lines. Rearrange x, which is equal to m lambda L over d, to solve for wavelength. Then rearrange c equals lambda f to solve for frequency. So go ahead and calculate that out, pause the video, and move on to the next slides to check your answer. Solving for lambda, we have this expression. For the first spectra, m is equal to 1, L and x are measured in the lab, and then d is calculated from the diffraction grating. Using all units in meters, except for m, which is unitless, the resulting wavelength will be in meters. Typically, the wavelength of light is given in nanometers, which is 10 to the 9th meters. Multiply the wavelength in meters by 10 to the 9th to convert it to nanometers. The equation for frequency is given on the lab, c over lambda. c is the speed of light, therefore meters should be used for lambda, because the speed of the light is given as 3 times 10 to the 8th meters per second. Hopefully you got these answers over here in red. If not, please go back and check your work. This is the wavelength of violet light, and this is its frequency. This will be the green light, and this will be the red light. A second data table is given for the data from the second spectra, where m is equal to 2. Please complete the table. The distance from the source to the grating, which is L, was changed in order to more clearly see the second spectra. So here's our distance from the source to the second order maximum. This stays the same, it's the same diffraction grating. So we're asking you to complete these two columns, pause the video, and come on back and check out the next slide for your answers. Upon initial inspection, we see that the values for the wavelength here are greater than they were for the first spectrum. That doesn't make sense. The wavelength of violet, green, and red should be constant. The average wavelengths for different colors are known values, and they're shown over here. The percent error can be found for your calculations. Here's your calculated lab wavelengths. So we'd like to calculate the percent error, which will be the average wavelength here, that's the accepted value, minus the calculated, divided by the average wavelength. You take the absolute value and multiply it by 100%. The percent error we calculate from our first data table, which is the first spectrum where m is equal to 1, are pretty good. 6.4%, 2.3, 7.7. Do the calculations for the second spectrum, please, and move on to the next slide when you're ready to check your answer. So pause the video if needed. Here's our percent errors for the second spectrum. Why are they so much worse than the first spectrum? Why might the first spectrum give us more accurate results than using the second spectrum, or why is the second spectrum calculations worse? Look at the diagram below. We can see that the second spectrum is at a greater angle. Here's your theta. Right, so they're at a greater angle than the first spectrum. When we formulated our equation, we used the small angle approximation. Our results should be better for the first spectrum because they are found at a smaller angle. Results for the first spectrum should come out to be fairly accurate. The variation in data will come from two main sources. The first is measurement. There will be some variation in the estimate of the central parts of the violet, green, and red parts of the spectrum. Also, if the meter stick is not aligned correctly with the light source, measurements will be off. The second is mathematical, the small angle approximation. The angle formed by L and X should be relatively small for the best results, and that happens, of course, when m is equal to 1. During the experiment, you can see the whole light spectrum by looking through the diffraction grating. That's because the amount of diffraction is dependent upon the wavelength of the light. The spectrum is organized by color, and you only see the colors at their maxima in the interference pattern. As diffraction and interference are thought of as wave properties, this lab shows that light is acting as a wave. Different students will arrive at different values for the wavelength of violet, green, and red light. The wavelengths of each color are known constants, but your answers will vary because of the limits of the human eye. We use inexact measuring tools to solve for a very small value, since wavelength is on the order of nanometers. You will see that as wavelength increases, the frequency decreases. This is important to note because the energy of light is frequency dependent. That means that higher wavelength light carries less energy.